You're good to go, John.
Okay, cool. So, hello, my name is Jonathan DeYoung, and it's been a pleasure to be the capstone design leader of this team this year. Thank you all for coming out. So, just by way of introduction, we have Wade Chaplin, Matthew Reed, Dana Hazelton, John Ruth, Dalton Callahan, Wyatt Ho, Duke Maley, and Zachary Fisher. And one thing that's really similar about all of us is that we're all Grovers, and so we like to do gear ratio optimization via electronic response. And that is the name of our capstone design project. So to kind of give you a better sense as to what gear ratio optimization via electronic response is, you should know what a continuously variable transmission is. So basically the way it works is that you have two pulleys, if you see from the video over on the right, and as they come together, it increases the radius of a V-belt, or decreases the radius of a V-belt. And that's what changes the gear ratios, as opposed to having big gears and small gears and so on, like a manual transmission. So in our current Baja car, we have something called a mechanical CVT. And looking down at this diagram here, you can see there's a couple of arms, and those arms are attached to one of the sheaves of the pulleys. And the pulleys rotate with the engine output shaft. So as the output shaft increases in RPM, the weights on the ends of the arms will pull out, and that will push against the cams that you see there, and that's what pushes the pulleys together. Okay? So typically it takes about 0.7 seconds for the pulleys to completely open and about 3.8 seconds for the pulleys to close. In order to optimize a system like this, we're going to switch out those weights depending on whether or not the car is going uphill, flat, or downhill. So typically the Baja team will go, okay, we want to do well going uphill, get the right power and everything, and so we're going to test out the car multiple times and figure out what that weight is. So the goal of our project is to get rid of those things and decrease the reaction time by using a computer, okay, as opposed to using the physics. The other thing we want to do is we want to optimize with any terrain. So instead of just picking one weight and rolling with it, instead we'll actually use a computer and control it for any type of terrain, whether going uphill, flat, or downhill. We have some other weight requirements. We want to decrease the weight of the overall car. So we want to have our weight of all the systems we're adding below 40 pounds. That's what the current weight of the components that we're trying to replace is. We want to provide gear ratios between 0.9 and 3.9 to keep it similar to the secondary, which we're not changing at all. That was the blue pulley halves that you saw in the diagram above. We want fast and easy assembly because out in the field, if something goes wrong, we want to be able to take it all apart really quickly. All right, and lastly, we need to comply with the SAE 2019 Baja rules. Otherwise, the Baja team will not be able to use our system. So just a brief overview, we're going to talk about the controller, we're going to talk about all the electrical inputs that go into it, such as the accelerometer, some motor speed, some brake switches, those sorts of things. We'll talk about our pedal design and how that interacts with the controller and how it allows the driver to vary his foot position, and that helps with us controlling how far the pulleys go back and forth. We'll talk about our mechanical actuation system, which is the actuation system that moves the pulleys. And then we'll also talk about our gearbox, which we've affectionately called Kevin.
So as far as selecting a controller, we had two large brands, both Arduino and MyRio. And our goals for either of them would be small size for a lightweight package. You saw the 40-pound goal that we were trying to shoot under. We also needed a sufficient number of input-output pins because we're going to be dealing with a very large sensor array so that we can tell the current condition of the vehicle and make the best decision possible for the output pulley distance for the best gear ratio. We also wanted to have minimal power consumption and sufficient memory on board to hold all of the code necessary. It also needed to be user-friendly because there's not a whole lot of electrical engineers on the Baja team, which is our customer for the product, so we needed it to be very simple for anyone with a rudimentary understanding of a little bit of code here and there to be able to hop on and use it. It also needed to be low cost because one of the factors that goes into the competition that this would be theoretically entered into is cost. It's a very large factor, so we wanted to keep that as low as possible. So here's a cost-benefit analysis of both the Arduino Dewey and the MyRio 1900. You can see right away there's a lot more green on the Dewey side. It is significantly cheaper, which was a huge benefit. It's also smaller and it weighs less, which they're both rather lightweight and small to begin with, but it also takes a fraction of the power. One of the first red sections you see is it has 10 less input-output pins, but even with the full size of our sensor array, which included the 6 thermocouples, which was the largest area that we scaled, it had plenty of pinouts. It's also more similar to C++ coding language, whereas LabVIEW runs on the MyReal, and generally speaking, because of the background in code and some of the intro level classes, pretty much any engineer that comes through Grove City is going to have a little bit of experience with code that's much more akin to C++ than they will have LabVIEW. And there's significantly less memory on the DUI, however, we did not run into any problems with fitting our code on the boards. So as far as attaching the controller to all of the rest of the pieces, there's the very large sensor array, which you'll hear from Dane in a moment, and then we'll be using that to take signals into the Arduino controller and then outputting a motor position, and that will be done through, this is the draft, the first prototype of our wire harness, which it's a mess. But it looks beautiful and visualizations are great. So as far as designing this wire harness, we had to take a look at all of the individual power requirements for each circuit, as well as where they'd be connected, the distance between those, and then we also selected colors. You don't want to have a bunch of random things that don't make any sense, which we have done in the past. So we also had to figure out what kind of connectors we were going to use, where the terminals pinouts were going to be, so that it's all documented, and when someone comes along and tries to fiddle with our stuff and doesn't understand it, it'll all make sense to them. We required some additional material like tape and means of fastening it to the Baja car frame itself, as well as protecting it. And here's just an example of our circuit layout table that has all of the, well, not all of them, but a breakdown of the different circuits that we had.
Yeah, so I'm going to go over the power system. As you can see from the diagram up top, the power system for the car consists of 3 main components: the alternator, a regulator, and a battery. Now, as John mentioned, SAE has certain strict rules that you have to follow for your vehicle. So in those rules, there are only 3 options for an alternator, of which we selected the most powerful that will give us about 30 volts of AC voltage out of it. We then paired the appropriate regulator with it. After going through the regulator, we'll have about 20 DC volts and 1 to 20 DC volts and 20 amps of regulated current. Now the final part of the power system is the battery, and what that does is it just kind of holds the charge that the alternator and regulator put out. So we just selected a small 12 volt 1.3 amp hour battery because it's not running off of the battery, it's being constantly charged by this alternator. So we did a few tests. These were our early tests on the alternator. We found that though it said you could get 30 volts AC out, at idle speed, which was the slowest speed that the car will run, we got about 11.5 volts out from just the alternator. And then going through the DC regulator, we got close to 8 3/4 to 9 volts. We did do in our final test, we found that the DC voltage coming out of the regulator was closer to 12 volts, which was more desirable. And that was at idle speed. And whenever it actually speeded up and we were at full speed, we got around 15 volts out of it. So what this is used to power is going to be the Arduino, like John mentioned before. And then these 2 things down here, which are our stepper drivers that help drive our stepper motor. And I'm going to go over those about right now. So we had 2 stepper drivers that we worked with. The first being the SN74, that's this chip. It's a quadruple half H drive. So what this chip does is it takes about 4.5 to 36 volts of DC voltage, which fits into our range. And each of these chips are about 1 amp a piece. So it takes around 5.6 amps to run our motor. So the small picture on the bottom right of the screen from the last time shows that it was kind of stacked. We used 9 of those in parallel to add the amperage together. And this requires about 200 steps per revolution. Versus a newer drive that we were working with due to heating problems of the chips overheating here, which takes 18 to 80 volts, which, as I said, ours wasn't getting up to that voltage, so what we would have to do is use a boost converter for this, which the only issue with that is adding another piece of equipment always adds another piece of failure that your product could have, though it seems like that is the approach that we need to go with. It takes up to 7 amps, which is fine with our motor, and has surge protection. The V in the name of it actually stands for vampire because it's literally unkillable, is what they say, which whenever you're having issues with a piece failing, and find something that's unkillable, that's usually pretty good. And this is also a 10 microstep drive, so that allows 2,000 steps per revolution, which gives you even more like ratios that you can achieve.
Yeah, so I'm going to dive into the sensors array, which is this huge block diagram right here. And I know it looks a little big, but we're just going to step through it and hopefully you'll understand it. So the first two sensors, as you can see, are the primary sensors. The first one being the engine speed sensor, the second one being the accelerometer. How the engine speed sensor works is there's a Hall effect sensor that measures magnetic field, and that is mounted inside the housing, which houses the flywheel in the engine. On the flywheel, there's a magnet mounted to the edge of the flywheel. Each time the flywheel spins around for one revolution of the engine, it sends a pulse through the Hall effect sensor to the controller. Those pulses can then be counted up, divided by duration of time, and that will give you your engine speed. The next sensor is the accelerometer. The accelerometer measures G-forces on the vehicle, and what it basically is a really small PCB, standing for printable circuit board, and it has 3 capacitors on it, one in the X direction, one in the Y direction, one in the Z direction. Those capacitors have a fixed side to them and a side that can flex ever so slightly. So as an acceleration force is applied to the PCB, one of those, the side that can flex, moves ever so slightly. As it moves, that changes the capacitance because the capacitor is actually changing the distance between them. That change in capacitance can then be converted through an algorithm to force being applied to the vehicle. The accelerometer is then mounted to the car frame closest to the center of gravity to give us the best readings. The next two sensors are the secondary sensors, which are measuring inputs directly from the user or the driver. The first sensor is very simple, brake sensor, which is you push your foot on the brake, it sends a signal to the controller. The second one is a throttle aggression sensor, which I'm going to talk about a little more after this, which basically measures how aggressive the driver is driving the car. The last set of sensors are monitoring sensors. 3 of them being thermocouples, which just measure temperature. There's one for the pulleys and the belt, making sure that that stays at a cool temperature. One for the DC motor, and one for the shroud, which is what covers the whole entire transmission. The last sensor is the pulley displacement sensor. That just tells you how far the pulleys in the transmission are apart relative to the angle of the stepper motor. So this is the throttle aggression sensor. On the top you have a standard pedal design, and like most cars, ATVs, that type of thing, where you push your foot on the pedal, pulls the throttle cable, opens up the engine. What we devised is a 2-stage pedal design. The first stage of it being exactly like the standard one. You push the pedal, opens the engine. Once the engine gets to 100% open, there's a stopper on the cable itself, and it hits up against the gate, preventing the driver from pushing the pedal further anymore. But what we did is we put a spring in series with it, which allows the pedal to be moved further without actually pulling the throttle cable any further. What that allows us to do is mount a magnet to the pedal, as you can see there, and another Hall effect sensor, which, as we said earlier, measures magnetic field. And as the pedal gets closer, the signal reads the magnetic field stronger, thus giving a larger input into the controller, and that allows the car to drive more aggressively. Now you're probably saying, what the heck does that mean? On most modern day cars, there is settings called eco mode and sport mode. And for those settings, they do a handful of different things with the engine, transmission, suspension. But as far as the transmission goes, if you're in eco mode for a car, it actually shifts the transmission sooner so you don't over rev the engine, giving you less torque, less acceleration, but better fuel economy. In sport mode, it actually shifts the transmission quicker, giving you more acceleration, a higher torque, and a worse fuel economy. So that is why we implemented this for the car. And the last question might be, why wouldn't you always want it in sport mode? Because sometimes you're not actually racing the car. You need to drive it around the track, you need to drive it to the track, you need to test it, you need to move it, and that is why you have the eco mode of it.
Now I'm going to walk you through some of the code we used for our project, starting out with the throttle aggression. Throttle aggression uses a linear Hall effect sensor, which detects the presence of a magnetic field, like they mentioned, and the signal changes proportional to the distance the magnet is away from the sensor. So it is on a scale from 0 to 254. That's the range, with a threshold set at 85. So anything below 85 would be the throttle position changing, and anything above 85 would change the gear ratio. Next slide. Now we'll talk about the engine speed sensor. We were the engine speed sensor, picture of it shown circled in red, is attached by a bracket right up next to the flywheel. We were originally planning to use wire windings wrapped around the spark plug cable and detect the current changes that way, but after extensive testing, we found that using this discrete Hall effect sensor would be simpler. It just acts as a on-off switch, so whenever the magnet's close to it, it flips on, whenever it's far away, it flips off. And again, we can count the number of revolutions and calculate the RPM. And finally, we have the stepper motor. The stepper motor is driven by data gathered from the sensor array on the car, and it directly correlates to the pulley position on the pulley sheaves. This code here shows a step function that simply increases or decreases the motor position relative to itself. And one of the challenges of this project was processing the data fast enough to keep up with the rapidly changing condition of the vehicle. Now I'll let Matt talk about the mechanical actuation.
Thanks. So I'm going to speak briefly on the mechanical actuation, what we actually used to drive the whole assembly. And also I'm going to touch briefly on some of the framing we used to construct everything and put it all together. So when we approached this problem, obviously we had to drive our CVT somehow, and we had, basically for the motor, we had a choice between what's called a servo motor and a stepper motor. A servo motor generally is a little bit more expensive and a little bit more difficult to drive, and also sometimes doesn't offer as much torque at a lower RPM, but it offers a little bit more accuracy when driving. A stepper motor, which is what we went with, is a little bit more powerful at lower RPMs. Tends to be a little bit cheaper and easier to drive as well. So ultimately, we went with this stepper motor right here that you can see. When deciding between the stepper motor and also the motor gearbox, we basically did some research, compiled a bunch of different options, threw them into a decision matrix, and then based off of things like cost and weight and size and such, we made a decision. One of the other things that we had to consider when assembling everything, we had to look at the link lengths that we would use for our crank rocker mechanism, which you can see over there. So one of the first and primary things we had to overcome was a 150-pound force, approximately 150-pound force, that we would be pushing up against when actuating the pulleys. So we did a test to determine that, but I'm not going to go into that right now. So in order to determine the optimum link length, a couple of members in our team assembled some MATLAB code, some tests, and use some things called chase equations, which some of you may or may not know or have nightmares about. But anyway, so these two graphs show the results of one of the tests. On the x-axis of both of these graphs, you have the input angle, which you can see on that diagram over there. So that was where we would start the actuation. And on this bottom graph, you have the y-axis showing output torque, and we need to reach a certain torque outcome. And then on the top graph, the y-axis shows the output displacement. Obviously, we had to have the pulleys actuate a certain distance to get the full range of motion. And a link length size of 1.5 inches or around that gave us all of the variables that we needed. It reached all of the objectives we needed. So one other thing we did is we had to assemble everything onto the car. And this plate that you see here is basically the backbone of the whole assemblage. Yeah. So you can see we ran some FEA analyses on this and put on some of the forces and torques that it would be going through during regular use, and we're able to refine the design as we went and lightened up.
So the system by which we transfer the load from the actuation crank linkages to the rotating pulleys we have dubbed the bearing interface. So the nature of our project and our mechanical system is that we have a mostly stationary actuation system with a crank just moving ever so slightly, linkages to follow, and a rotating pulley set, rotating at engine speeds, which can max out for anywhere from 3,000 to 4,000 revolutions per minute. So when you're pushing something on a mechanism, it's fairly simple. When you're pushing something at a 150-pound load, and the thing that you're pushing is rotating at speeds up to 4,000 RPM, it gets a little bit trickier. But not to worry. Next slide. Our design involves a deep groove ball bearing, which you can see in the gray inside of the red housing. A deep groove ball bearing was chosen over something like a standard shaft ball bearing because a deep groove ball bearing is rated for both axial and radial combined loads. Since the majority of our load that we're putting on this bearing is axial, we needed something to accommodate that. The bearing is housed inside of a low carbon steel red part housing, not the pulley, but the red part housing secured by a plate cap. This is seated in as a transition fit inside of the housing so as to make service and assembly much easier. But we had to coat the outside of the outer race with an adhesive coating in order to keep it secure. So that holds the outer race in place, while the inner race is press fit onto the boss feature of the blue pulley, which will rotate along with the pulley and the shaft at engine speeds. This allows the bearing to be the push and the pull of the system, allowing the linkages to push and pull the housing, the bearing, and the blue pulley along the keyed shaft. Our parts were made using Bridgeport and CNC milling capabilities in-house, all of them except for the bearing itself, which we selected and purchased from an outside vendor.
All right, so putting this whole thing together, we get something that kind of looks like this. So you can see in there you have the winged parts, you have some 80/20 that's holding it and attaching it to the car itself, and you'll see the interface and the pulleys on the inside, and we'll show you some more pictures of that in a minute. The total weight of this system, including the gearbox that we'll talk about in a bit, weighs 28.5 pounds, which if you remember to the beginning of our presentation, we wanted it to be below 40 pounds. So this is a huge difference that we managed to get. It's 10 inches by 14.6 by 8.5, which means that it fits beautifully within inside the cage and within inside the suspension and everything that it needs to fit inside of. The pulley gear ratios are between 0.9 and 3.9, just as we had specified at the very beginning of this project. And then also the shroud covers all the safety requirements that they have outlined in B9.2, which is a 33 millimeter minimum thickness of that shroud. And you can kind of see the shroud surrounding our entire system there. That's to keep stuff, if something should break, from flying out and hitting people that are standing around. So we managed to run a big test on this project. And what we did is we basically put the entire thing onto the car frame, and then we set the frame on a table, and then we pulled the engine, started the engine, had the engine running at 1400 RPM, and what we found is that the deep groove ball bearing that Duke mentioned held up just fine. It was around 135 pounds of force. Disassembly and assembly of the whole system when we were putting it together took under 5 minutes, which meets our criteria of being out in the field. If something breaks, we have to be able to take this thing apart. So basically the way we take it apart is we pull off the 3 screws that were on that winged plate that Matthew was talking about. We pull out 2 cotter pins, which you can see right in here, and then you would pull off these bolts off the primary and off the secondary. So a total of 5 bolts and 2 cotter pins. So I think that's pretty good. And then we can also take this thing completely apart with the suspension in front of it. So we don't have to take off the suspension at all to fix any of this. Our throttle system effectively does adjust the gear ratio, the throttle system that Dane was talking about. So we were able to push the pedal a little bit back and forth, and we were able to see that the pulleys stayed a certain distance up until we hit the spring, and then as we pressed the pull on the spring, then the pulleys started to close together, which was that eco sport mode and that sort of thing. So it worked just as we thought it would. And then the actuation speed is 0.45 seconds, which is a lot faster than the 0.7 seconds and the 3.8 seconds that we talked about before. So this thing operates a lot quicker. Some current problems we have, however, are that the H-bridge, which we used, has some heating issues. It ended up blowing during the middle of this test, and so that's why we were looking into the Gecko drive that Dalton talked to you about later, but that is also a current problem that will have to be fixed in the future. Some other things is that we haven't put the code that we had talked about with the mechanical system yet due to the amount of time it took for the mechanical system to be built, and some other setbacks that we had. So in the future, going forward, the Baja team will have to put the two together. And we're confident that we're at a good spot where they can do that pretty easily. And with that, we're going to go to our Kevin, which is our gearbox.
Yeah, so as Jonathan mentioned, second side of our project was to design and manufacture a new gearbox for the Baja car. The gearbox takes the output from the ECVT, reduces the speed to provide more torque, and then transmits power to the rear axle of the vehicle. The new gearbox, the goals with that were to target and improve on several issues with the old gearbox on the Baja car. The first of those being that it was a 2-speed gearbox and it was prone to slipping out of gear. So our solution to that was to create a single-speed gearbox that we knew would never be able to slip out of gear because there's only one speed, and it would also be able to reduce weight significantly. The second problem with the old gearbox was that it leaked oil. So the solution was to have a simple case design with better contact surfaces when it was closed up so that it would more effectively seal in the oil. Lastly, the problem with the old gearbox, which you can kind of see on the left, is that it was really heavy. It weighed just under 30 pounds. So the new design, one of our biggest goals was to cut weight as much as we possibly could, and we were successful in doing that as it came in under 10 pounds. So the first step in creating the gearbox was the gear design. The first part of that was calculating the gear ratio. The main parameter of that was your desired speed range that we wanted to hit, and a number of other parameters. The second part of the gear design was calculating the forces on the gears. We did this using a spreadsheet that had equations with AGMA gear standards, calculations that we learned about last year in class. Essentially, you put in a bunch of parameters and you get out the worst case scenario forces based on inputs like engine horsepower and the RPM of the gear. So there's 4 gears total, and we got the worst case scenario forces that each gear would undergo. And then once we had those forces, we were able to use Dr. Archibald's Creo program to get just our base CAD models of the gears. So from there, once we had the base CAD models and the forces, we were able to run FEA on the gears to verify that those initial CAD models would hold up under the loads we were going to experience. The next step from there was optimizing the gears for weight by removing material and then iteratively analyzing them using FEA to make sure that they would hold up despite having less material on them, and that was how we were able to cut off as much weight as we possibly could.
Alright, so the next step was sizing the bearings for the transmission. To effectively size bearings, you need to know the forces that are on the bearings, which we calculated with the spreadsheets Wade was talking about. And you need to know the lifespan you're shooting for. So from the Baja team, we determined that 80 hours would be a reasonable life for this transmission to last with the bearings in it. So we created this spreadsheet which calculated a C10 force, which basically tells you your smallest bearing that you can use that will survive 80 hours with the forces given. We used Shigley's bearing life calculations to come up with that Excel spreadsheet. So after we had the smallest possible bearings that we could use without failure, we decided to design the shafts. The shafts were designed to minimize weight while still maintaining durability. So we decided to use large diameter shafts with large holes cut in the center. And the reason for that is a large hollow shaft is much stronger per weight than a smaller solid shaft. Other considerations that went into shaft design were where everything had to sit on the shafts. You're oftentimes press fitting many different components on. So all of your bearings, your gears, and in this case a brake disc all have to slide on properly and need to be located so that they can't walk back and forth through vibration. We also had material considerations. The 2 outside shafts, as you can see here, were manufactured out of 4140 steel because they had sliding forces on them, so they needed to be durable with a sliding load. The center shaft, however, was only under torque and a bending load, so we decided to make it out of titanium to save weight. So now that we have bearings, shafts, and gears, we can start our case design. The case basically designed itself because we had certain parameters that we needed to meet. We needed an oil drain plug, we needed large sealing surfaces so it didn't leak, and we needed to locate all of our components precisely. So the only part that was specified by the 2019 Baja rules is a powertrain guard, which has to go around the entire outside of any rotating components and needs to be 3 millimeters thick. So all of those factors were assessed and weight was removed where we could to make everything as thin as possible. After we had our thinnest case, we analyzed it with FEA and determined that it didn't need any additional reinforcing to withstand the loads we were anticipating. So this is the final design we came up with. The transmission will last 80 hours before needing a rebuild. A rebuild includes new seals, new bearings, and all the gears need to be checked for signs of fatigue. Every component in this transmission has a 1.5 minimum safety factor. The transmission weighs 9.5 pounds fully assembled and is geared to allow our vehicle to travel 42 miles an hour. To do some testing on this, we ran the vehicle over railroad ties, which kicked the back end up in the air. Anytime the rear end of the vehicle comes up in the air and then lands with torque still being applied to the wheels, it creates a massive shock loading, so we wanted to make sure our vehicle could withstand that. We also ran 20+ runs where we just positioned the vehicle from a dead stop, applied maximum engine torque, and basically saw what happened. So now we're on to our finance section. This is our sensitivity analysis. You can see our different categories as a percentage of total project cost. And this is our Pareto chart, which demonstrates that as our project neared completion, the amount of money we spent increased, making it difficult to go back and affect design changes.
Questions for them?
Yeah, I have one.
Yeah.
80 hours didn't seem like a very long time between rebuilds. So did you choose that just to minimize weight, or what was the reason for that?
It was chosen to minimize weight. The Baja vehicle, if we go to 2 competitions a year, we typically run the vehicle for less than 8 hours at each competition. There's a 4-hour endurance race, which is continuous, and then just various static testing stuff. So we decided that 80 hours would be a reasonable lifespan for the transmission.
If I could just toss this out there for a fun fact, some of the larger teams that have budgets that are significantly higher than ours, like RIT, they design their gears to last 8 hours for one competition apiece. They just slap a new one in there every time. So their gears are like little tiny things that weigh basically nothing.
Yeah.
What was the material of your gear case?
6061.
And then the gears themselves?
The gears were made out of hardened 4140.
So did you buy the gears?
We manufactured everything you saw in-house. The gears were cut on our wire EDM and our Fadal. It's 3x60.
And if Jim was here, we'd all give him a round of applause because he did a tons of work on all of the different stuff that we had here. So his work is much appreciated, but he couldn't make it, I guess.
We chose the 6061 over something like a 7075, which would be stronger, just because we didn't need the strength. We made it as thin as the rules would allow,
Right.
and the cheaper material was strong enough. So.
Brian, you had a question?
Yeah, back to Jack's point. What, of course, the proof was running at full throttle and then hitting the ground, but what safety factors, I saw your graph, but what safety factors were you shooting for when you were looking at key stress and things like that.
Yeah, we did not analyze our keys as well as we should have. We actually broke a key rather, but we believe the key was made out of a mild steel, and we're looking into high strength steel alloys for that. We created a 3D printed scale model of the transmission, and we tried putting a torque into our 3D model to see where the gears would fail, because we didn't have budget to break actual components. But if we could have made multiple transmissions and test them to failure, we would have done that.
Okay, thank you, folks. All right, one more, then we gotta go.
We can take
Yeah, I'm
one.
sorry, I love the name of the grower. So just a comment there, and none of you are named Kevin?
No.
So I think you can
Well,
tell
they
us-
did start off with 10 team members, so.
How did you get Kevin?
Is that my
That's
question?
your question.
All right, so whenever we were talking about like what we wanted to name it, I think I was sitting in Hoyt lobby across from like Dane and like our EE team was meeting. I was like, we should just name it something weird like Kevin and like make an acronym for it. But we couldn't come up with a cool acronym for Kevin, but we could for the Grover, so we decided to name the gearbox Kevin in honor of the fact that we couldn't actually come up with an acronym. So.
All right, thank you, guys.
All right.